rocket engine burns fuel at a rate that would drain an Olympic swimming pool in under 60 seconds. It generates temperatures 3 times hotter than the surface of the sun. And it does all of this while producing enough thrust to lift a structure taller than the Statue of Liberty off the ground and accelerate it to 28,000 kilometers per hour. How does burning fuel in a metal chamber produce enough force to escape Earth's gravity? How does an engine survive temperatures that would vaporize any known metal if it touched the walls? And why does the most powerful rocket engine ever built consume more propellant in 30 seconds than a commercial airliner burns in an entire transatlantic flight? The answers involve physics that most engineers consider borderline miraculous, cooling systems that use the fuel itself as a refrigerant, turbopumps spinning faster than a Formula One engine at maximum RPM, and combustion chambers operating at pressures high enough to crush a nuclear submarine hull. You have watched rockets launch. You have never understood what is actually happening inside the engine. That changes right now. Let's start with the raw numbers, because the scale of a large rocket engine redefines what the words power and force actually mean. The SpaceX Raptor engine, currently the most powerful rocket engine in operational use, generates approximately 230 metric tons of thrust at sea level. 230 metric tons of thrust. That is the equivalent of 230 fully loaded garbage trucks being pushed simultaneously from below by a single engine the size of a small car. The Raptor achieves this by burning liquid methane and liquid oxygen at a combined flow rate of approximately 650 kilograms per second, enough propellant to fill a standard bathtub in under half a second. The Raptor operates at a combustion chamber pressure of approximately 300 bar. 300 bar, that is 300 times normal atmospheric pressure, 3 times higher than the pressure rating of most nuclear submarine hulls, which are designed to withstand the crushing force of deep ocean water. The Raptor achieves the highest combustion chamber pressure of any rocket engine in production history. The combustion temperature inside the Raptor's main chamber reaches approximately 35.0 degrees Celsius. 35.0 degrees Celsius. The surface of the Sun measures approximately 5778 Kelvin, roughly 55.5 degrees Celsius. The Raptor's combustion temperature reaches approximately 64% of the Sun's photosphere temperature, sustained continuously inside a metal structure small enough to fit in a standard garage. The Saturn V rocket, which carried Apollo missions to the Moon, used 5 F-1 engines, each producing 680 metric tons of thrust. 5 F-1 engines combined produced 34.0 metric tons of total thrust at liftoff. That is enough force to lift 34.0 fully loaded garbage trucks simultaneously, from a standing start on a launch pad to 100 kilometers altitude in approximately 12 minutes. The Saturn V's F-1 engines consumed approximately 12,710 kilograms of propellant per second during full operation. 12,710 kilograms per second. That is the combined weight of approximately 8 mid-size passenger cars, consumed as fuel every single second of operation. The Saturn V burned through its entire first stage propellant load 2.1 million kilograms of kerosene and liquid oxygen in approximately 165 seconds of flight. The SpaceX Starship Super Heavy booster uses 33 Raptor engines simultaneously. 33 Raptor engines firing together produce approximately 90 metric tons of total thrust, more than double the Saturn V's total thrust. This makes the Starship Super Heavy the most powerful rocket vehicle ever flown, producing more thrust at liftoff than any launch vehicle in the history of spaceflight. The specific impulse of the Raptor engine, a measure of fuel efficiency equivalent to miles per gallon for rockets, reaches approximately 363 seconds in vacuum conditions. 363 seconds specific impulse. For comparison, the best chemical rocket engines of the 1960s achieved approximately 260 seconds. Every additional second of specific impulse translates directly into more payload delivered to orbit for the same amount of propellant mass. So how does burning propellant in a chamber actually produce force capable of lifting thousands of tons? The physics is elegant and brutal simultaneously. Newton's third law is the foundation. Every action produces an equal and opposite reaction. When high-pressure combustion gases are forced out of a rocket nozzle at extreme velocity, the reaction force pushes the rocket in the opposite direction. The rocket does not push against the ground or the air or any external surface. It pushes against nothing. The exhaust going one direction is the only mechanism. Think of it like holding an inflated balloon and releasing the opening. The air rushes out in one direction. The balloon accelerates in the opposite direction. A rocket engine is this principle scaled up by a factor of several million. The key variable is exhaust velocity. The faster the exhaust exits the nozzle, the more force is produced per kilogram of propellant burned. Exhaust velocity in a Raptor engine reaches approximately 35 meters per second, roughly 10 times the speed of sound at sea level, exiting a nozzle the width of a large dining table. The nozzle shape is critical to achieving this velocity. A convergent-divergent nozzle, called a de Laval nozzle, accelerates hot combustion gas by first compressing it through a narrowing throat section, then allowing it to expand through a widening bell section. In the throat section, the gas reaches exactly the speed of sound, Mach 1. In the expanding bell section, the supersonic gas accelerates further as it expands. By the time it exits the nozzle, it is traveling at Mach 10 or faster depending on nozzle expansion ratio. The nozzle converts thermal energy, heat from combustion, into kinetic energy, directed velocity of exhaust gas, not through any moving parts, purely through geometry. Surprising fact number 1. The Raptor engine's turbopump spins at approximately 90,000 RPM, 90,000 revolutions per minute. A Formula One engine at maximum legal RPM reaches approximately 15,000 revolutions per minute. The Raptor's turbopump spins 6 times faster than the most finely engineered racing engine in the world, while simultaneously handling liquid methane at -161 degrees Celsius and hot combustion gases at several hundred degrees, within the same rotating assembly. Surprising fact number 2. The combustion chamber of a high-performance rocket engine does not melt because it is cooled by the propellant flowing through it before combustion. The Raptor uses a method called regenerative cooling. Liquid methane, at -161 degrees Celsius, is routed through thousands of tiny channels machined into the walls of the combustion chamber and nozzle, absorbing heat from the chamber walls before being injected into the combustion zone and burned. The fuel that will eventually combust at 35 degrees is simultaneously keeping the chamber walls at survivable temperatures by flowing through them first. The engine is cooled by its own fuel while being destroyed by its own fire. Surprising fact number 3. Rocket engines are deliberately run fuel-rich, meaning more fuel than oxygen, to protect chamber walls from oxidation damage. At perfect stoichiometric combustion, the chemically ideal fuel-to-oxygen ratio, the combustion products would be highly corrosive to metal surfaces. By running approximately 10 to 15% fuel-rich, the combustion environment becomes less chemically aggressive toward the chamber walls. This costs a small amount of efficiency, but dramatically extends engine life and structural integrity during operation. Here is where rocket engine engineering becomes genuinely extreme, because the systems keeping the combustion alive, fed, and controlled push materials science and mechanical engineering to their absolute limits simultaneously. The turbopump system is the critical challenge. At sea level, the propellants, liquid oxygen and liquid methane or kerosene sit in tanks at relatively low pressure. The combustion chamber requires them at 300 bar of pressure. moving propellants from near-atmospheric pressure in the tanks to 300 bar in the chamber requires a pump of almost incomprehensible power density. The Raptor's turbopump assembly produces approximately 100,000 horsepower. 100,000 horsepower from a pump small enough to hold in both arms. For comparison, the Titanic's entire steam propulsion system produced approximately 46,000 horsepower to move an 52,000-ton ship across the Atlantic. The Raptor's turbopump produces more than twice that power output in a package weighing a few hundred kilograms. This turbopump power comes from burning a small fraction of the propellant in a pre-burner, a smaller combustion chamber specifically designed to generate hot high-pressure gas that drives the turbine blades of the pump. In the Raptor's full-flow staged combustion cycle, both propellants pass through separate pre-burners before reaching the main combustion chamber. The oxidizer-rich pre-burner burns oxygen-rich gas to drive the oxygen turbopump. The fuel-rich pre-burner burns methane-rich gas to drive the methane turbopump. All combustion products from both pre-burners then flow into the main combustion chamber. Nothing is wasted. This is why the full-flow staged combustion cycle achieves the highest theoretical efficiency of any liquid rocket engine architecture. The materials challenge is equally extreme. Turbine blades inside the turbopump experience centrifugal forces at 90,000 RPM, equivalent to approximately 150,000 times the force of gravity, pulling on each blade outward from the rotation axis. The blades must survive this centrifugal loading while simultaneously being bathed in combustion gases at several hundred degrees. Modern turbine blades in rocket engines are cast as single crystal metal structures, meaning the entire blade is one unbroken crystal of nickel superalloy with no grain boundaries. Grain boundaries in metals are weakness points where stress concentrations occur under cyclic loading. Eliminating grain boundaries entirely by growing the blade as a single crystal increases fatigue resistance by factors of 3 to 5 compared to conventionally cast metal. A technology originally developed for military jet engines in the 1960s is now standard in rocket turbopumps. The combustion stability challenge deserves specific attention. Combustion instability, uneven burning patterns in the chamber, generates acoustic resonance that can destroy an engine within fractions of a second. The F-1 engine development program in the 1960s was nearly terminated by combustion instability problems. Engineers detonated small explosive charges inside firing engines to understand the acoustic patterns, then redesigned injector plate geometry to shift resonant frequencies out of the dangerous range. The process required over 2,000 engine tests and consumed more development money than the original engine design. Combustion instability remains one of the hardest problems in rocket engine engineering. It cannot be fully simulated computationally and must be discovered and resolved through physical test firing. The ignition system of modern methane engines uses a torch igniter, essentially a miniature rocket engine firing into the main combustion chamber to initiate the primary combustion event. The torch igniter itself requires ignition, typically by an electrical spark igniter firing into the torch igniter's own propellant supply. An igniter for an engine. Each layer of this ignition sequence must fire in the correct order within milliseconds, at cryogenic temperatures, in a chamber that goes from inert to 300 bar of combustion pressure in under 1 second. Engine startup, the sequence from ignition command to full thrust, takes approximately 1 to 3 seconds in a modern high-performance engine. During those 1 to 3 seconds, propellant flow rates, combustion chamber pressure, and turbopump speeds all ramp from 0 to full operational values, while control systems actively monitor hundreds of sensor readings and stand ready to trigger emergency shutdown if any parameter deviates beyond defined limits. Shutdown is even more critical than startup. When a rocket engine is commanded off, residual propellants must be purged from the combustion chamber and turbopump before they freeze, react chemically, or detonate. The shutdown sequence involves precisely timed valve closures that prevent propellant mixing in the wrong zones during the depressurization event. A shutdown sequence error can destroy an engine in milliseconds. Now let's get into the facts that most people who have watched rocket launches have never known. First, the white cloud that erupts from the launch pad during liftoff is not smoke from the rocket engines. It is steam. Most launch pads use massive water deluge systems, releasing hundreds of thousands of liters of water per second onto the launch structure and flame trench in the seconds around ignition. This water absorbs acoustic energy from the engines, sound waves powerful enough to physically damage the rocket's structure if not suppressed, and the water instantly vaporizes into steam on contact with the flame. The Saturn VS launch pad water deluge system released approximately 1.1 million liters of water in the first 30 seconds of ignition, enough to fill an Olympic swimming pool in under 40 seconds. The enormous white cloud surrounding the rocket at liftoff is almost entirely water vapor, not combustion products. The actual flame from the engines is largely invisible against it. Second, rocket engines are tested on the ground before being installed in a rocket, and these test firings are deliberately pushed to destruction. NASA and SpaceX conduct planned engine destruction tests, running engines beyond their rated performance limits until they fail, to understand failure modes and validate safety margins. A single Raptor engine test costs approximately $1 to $2 million. SpaceX has conducted hundreds of such tests at their facility in McGregor, Texas, where the test stand flame trench is visible from aircraft flying over the area. Third, the flame from a vacuum-optimized rocket engine would extinguish itself at sea level. Rocket nozzles are designed for a specific ambient pressure environment. A vacuum-optimized nozzle, designed for operation above Earth's atmosphere, has an expansion ratio that allows combustion gases to expand so completely that the exhaust pressure at the nozzle exit falls below atmospheric pressure at sea level. At sea level, the higher ambient pressure would collapse the exhaust plume inward, disrupting the combustion pattern and extinguishing the engine. This is why upper stage engines with large expansion ratio nozzles cannot be test-fired at sea level and require either vacuum chambers or altitude simulation facilities. Fourth, the Merlin engine used in SpaceX Falcon 9 rockets has been restarted in flight over 170 times across the fleet, demonstrating reusability at a scale no previous rocket engine achieved. The Merlin 1D engine produces approximately 91 metric tons of thrust and burns Rp-1 kerosene with liquid oxygen. After stage separation, the first stage Falcon 9 performs a re-entry burn and landing burn using 3 and then 1 Merlin engine respectively, decelerating from approximately 2,000 meters per second to near zero velocity for a propulsive vertical landing. The same engine that launched the rocket performs precision throttling from 40% to 100% thrust within milliseconds during the landing sequence. A control authority no previous production rocket engine demonstrated consistently. Fifth, and here is the controversial part, the most powerful rocket engine ever designed, the Soviet RD-170, was never used in a successful orbital mission and remains in limited production today, despite being technically superior to most Western engines by several performance metrics. The RD-170 produces approximately 806 metric tons of thrust from a single engine, more than 3 times the thrust of a single Raptor, and more than the entire thrust of a Falcon 9 rocket. It uses a staged combustion cycle with 4 combustion chambers fed by a single turbopump assembly, achieving a specific impulse of 337 seconds at sea level, exceptional performance for a kerosene engine. The engine was developed for the Soviet Energy rocket program, which flew only twice before the Soviet Union's collapse ended funding. Russia continues producing a derivative, the RD-180, which the United States purchased for use in Atlas V rockets until political tensions over Ukraine led to U.S. legislation mandating replacement with American-designed engines. American aerospace engineers who have examined RD-170 and RD-180 engines have publicly stated that Russian liquid rocket engine manufacturing techniques, particularly turbopump construction and combustion stability management, remain technically advanced beyond equivalent American production capabilities in several specific areas. The debate over whether American engine development programs have fully closed this gap is ongoing within the aerospace engineering community. So here is what actually happens inside a rocket engine, assembled into its complete picture. Liquid propellant stored at -161 to -183 degrees Celsius are pressurized from near-atmospheric tank pressure to 300 bar by a turbopump spinning at 90,000 RPM, producing 100,000 horsepower in a package the size of a small refrigerator. Those propellants flow through thousands of channels machined into chamber walls, cooling metal surfaces that would otherwise vaporize, before being injected through hundreds of precisely angled orifices into a combustion zone burning at 35 degrees Celsius. The resulting gas expands through a convergent-divergent nozzle, accelerating from 0 to Mach 10 in a distance shorter than a human arm, and exits at 35 meters per second to produce thrust through Newton's third law against the vacuum of space. Every component in this system operates at the intersection of multiple simultaneous extreme conditions: cryogenic temperatures and extreme heat, maximum mechanical stress and zero tolerance for material failure, chemical aggression and precision geometry. All of it happening continuously at 300 bar for the duration of the burn. The Raptor engine completes its primary mission in approximately 3 minutes of full-thrust operation for the first stage of a Starship launch. 3 minutes. In those 3 minutes, 33 Raptor engines working together consume approximately 3.2 million kilograms of propellant, generate 90 metric tons of thrust, and accelerate a structure 120 meters tall and 5,000 metric tons in mass from 0 to approximately 24 meters per second, fast enough to cross a continent in under an hour. Here is the question worth sitting with. If engineers have built engines that burn at 3 times the temperature of any known metal's melting point, spin turbines at 6 times Formula 1 RPM limits, and pressurize propellant to 3 times the rating of nuclear submarine hulls, all in a package that fits in a garage, what does that tell us about what engineering extremes are actually achievable when the mission demands it? Maybe the real lesson from rocket engine development is not about any single technology. Maybe it is that the absolute limits of what materials, thermodynamics, and mechanical engineering can deliver are almost always further than current consensus believes, until someone needs to push past them. If this changed how you see the world, hit subscribe. We uncover the truth behind things you thought you already knew. Right now, a Raptor engine is being test-fired in McGregor, Texas. 300 bar of combustion pressure, 35 degrees Celsius, 90,000 RPM. The test stand is shaking the ground for kilometers in every direction. In 3 minutes, it will be over. The engine will be ready to fly again.